Automaticity. Automaticity refers to the ability of the cell to generate an impulse. In the sinoatrial node P cells and the atrioventricular node N cells, spontaneous diastolic depolarization starts at the end of phase 4 of the action potential, decreasing the resting membrane potential until it reaches the threshold potential, then a new action potential is fired. These cells are thus called automatic fibers. On the other hand, if the resting potential failed to reach the required threshold, it will die out, failing to fire an action potential. If the resting membrane potential reaches the threshold potential, a new action potential is fired, blue curve. If it fails to reach the required threshold, it will die out, failing to fire an action potential, red curve. Ionic currents in the automatic fibers. Automatic fibers are characterized by activated sodium and calcium inward currents, with delayed potassium outward current, resulting in a net inward current, that is, depolarization. Not only sinoatrial and atrioventricular nodal cells are automatic, but other tissues of the conduction system down to the His Purkinje fibers are also automatic, albeit their rate of firing is much slower. Pacemaker of the heart. The sinoatrial node possesses a maximum rate of firing of 200 beats per minute, which decreases gradually down the conduction system, thus the maximum rate of firing in the Purkinje fibers is only 120 beats per minute. The sinoatrial node is the pacemaker of the heart, which in the absence of extrinsic neural and hormonal control, will naturally discharge at about 100 impulses per minute. Normally, however, the vagal tone markedly decreases the rate of firing at all levels. The sinoatrial node in the resting adult usually discharges at about 70 beats per minute. Other automatic fibers in the heart. Other specialized atrial tissues may also possess automaticity, such as fibers along the crista terminalis, fibers near to the eustachian valve, valve of the inferior vena cava, fibers near to the coronary sinus orifice, fibers near to the tricuspid and mitral valve rings. Non-automatic fibers. Working contractile atrial and ventricular myocardial cells are called non-automatic fibers, because they do not normally have spontaneous diastolic depolarization in phase 4, and do not initiate spontaneous impulses, even if no impulses excited them for long periods. Non-automatic fibers can, however, fire an action potential, when stimulated by external impulses, and also under pathological conditions, which reduce their resting potential to a less negative level. In such cases they become automatic, but the automaticity under these conditions is called abnormal automaticity. Abnormal automaticity in which fibers? Abnormal automaticity can occur in non-automatic fibers, under pathological conditions, which reduce their resting potential to a less negative level, and in automatic fibers, under physiological or pathological conditions, which augment their automaticity. This type of abnormal automaticity is called enhanced or accelerated automaticity. Automaticity, normal or abnormal. The most characteristic feature, which distinguishes normal from abnormal automaticity, is the level of membrane potential, at which spontaneous diastolic depolarization occurs. In normal automaticity, spontaneous diastolic depolarization occurs at the fiber's own intrinsic resting potential, and under normal physiological conditions. In abnormal automaticity, however, spontaneous diastolic depolarization does not occur, until the fiber is depolarized to a level that is less negative than its own intrinsic resting potential. Abnormal automaticity does not also occur, except under abnormal physiological, or pathological conditions. Another important feature characteristic of abnormal automaticity is that the smaller or less negative the magnitude of the membrane potential, from which firing occurs, the faster the rate of firing. This figure shows that firing from a smaller potential results in a faster firing rate. There are many causes of abnormal automaticity, most importantly sympathetic stimulation and sodium pump inhibition, resulting in a net inward current through the sodium channels, such as occurs in digitalis toxicity, hypokalemia, hypoxia, ischemia, and fiber stretch. Effect of cardiac pacemaker on other tissues. The pacemaker of the heart is the automatic fiber which has the most rapid rate of firing, naturally, the sinoatrial node. The cardiac pacemaker depolarizes all other foci, which are called latent pacemaker cells, preventing them from initiating impulses, because they are repeatedly depolarized, before they have a chance to fire, a phenomenon known as overdrive suppression. Driving latent pacemaker cells, faster than their intrinsic spontaneous rate, increases their intracellular sodium concentration, since sodium is repeatedly entering the cells, during each action potential upstroke. As a result, the sodium pump is activated, which prevents intracellular sodium from rising to very high levels, although there is some increase in the steady-state sodium concentration. Since the sodium pump moves more sodium outward than potassium inward, it generates a net outward current across the cell membrane, which hyperpolarizes the membrane potential and suppresses spontaneous impulse initiation in these cells. Overdrive suppression can be demonstrated by suddenly stopping the sinoatrial node, for example, by vagal stimulation. Impulses then usually arise from a latent pacemaker, but this is generally preceded by a long period of quiescence, followed by impulse initiation at a low rate, and gradually speeding up, to a final steady rate, that is still slower than the original sinus rate. When the dominant pacemaker is stopped, the suppression continues, because the sodium pump continues to generate the outward current, to reduce the intracellular sodium levels, towards normal. The continued current is responsible for the period of quiescence, which lasts until the intracellular sodium concentration becomes small enough, to allow latent pacemaker cells to depolarize spontaneously to threshold. During the quiescent period, intracellular sodium concentration continues to decrease, because sodium is constantly being pumped out of the cell, causing a gradual increase in the discharge rate of the latent pacemaker. Escape. Escape of other foci from sinus node suppression can occur under abnormal conditions, such as sinus slowing and sinoatrial block, in which cases any supraventricular or ventricular focus, having a higher rate of firing, may take over cardiac pacing. Atrioventricular block, in which only ventricular foci can escape, generating an idioventricular rhythm. Protected focus, not affected by sinus impulses. Enhanced automaticity of ectopic foci, exceeding sinus firing rate. Overdrive suppression of the sinus node itself. The sinus node itself can also be overdrive suppressed if it is driven at a rate faster than its intrinsic rate. Thus, there may be a quiescent period, after termination of either overdrive pacing, or a rapid ectopic arrhythmia, before the sinus rhythm resumes. Relative resistance of the sinus node. The sinus node action potential upstroke is largely dependent on slow inward L-type calcium current, and far less sodium enters the fiber during the upstroke, than in latent pacemaker cells. Consequently, the activity of the sodium pump is probably not increased to the same extent in the sinus node, after a period of overdrive, therefore, there is less overdrive suppression. Sinus node usually remains the pacemaker. The relative resistance of the normal sinus node to overdrive suppression may be important in enabling it to remain as the dominant pacemaker, even when transiently affected by external influences. The diseased sinus node, however, may be much more easily overdrive suppressed. Electrotonic interaction. Another mechanism that may suppress latent pacemakers is the electrotonic interaction between the pacemaker and non-pacemaker cells. The electrotonic potential is a local potential, resulting from a local change in ionic conductance. This mechanism may be particularly important in preventing the atrioventricular node and the distal Purkinje system automaticity. Determinants of the pacemaker firing rate. The pacemaker firing rate depends on magnitude of the resting membrane potential, slope of diastolic depolarization of phase 4, that is the angle of depolarization from the resting potential. The bigger the angle, the faster the slope of rise, and vice versa. Magnitude of the threshold potential. Action potential duration. This is a schematic, showing how the membrane potential decreases, from the resting, RMP, to the threshold potential, TP, with the slope or angle in between, that determines the speed of this change. The bigger the angle, the faster the slope of rise, and vice versa. Magnitude of the resting membrane potential, RMP. The more negative the RMP, increased magnitude, the longer the time it takes to reach the threshold potential, thus reducing the firing rate, for example, with vagal stimulation. Less negative RMP produces the opposite effect. In this figure, RMP1 is less negative, it takes shorter time, T1, to reach the threshold potential, TP. RMP2 is more negative, it takes longer time, T2, to reach the TP. Slope of phase 4. The more rapid the spontaneous depolarization, increased slope of phase 4, the shorter the time to reach the threshold potential, thus increasing the firing rate, for example, with ischemia or sympathetic stimulation. Reduced slope, for example, with vagal stimulation and hypothermia, reduces the firing rate. Slope S1 is faster, it takes shorter time, T1, to reach threshold potential, TP. Slope S2 is slower, it takes longer time, T2, to reach threshold potential, TP. Magnitude of threshold potential. The more negative the threshold potential, the shorter the time it will be reached, thus increasing the firing rate, for example, with hypercalcemia. With less negative threshold potential, the firing rate is reduced, for example, with hypocalcemia. Threshold potential TP1 is more negative, it is reached in a shorter time, T1. Threshold potential TP2 is less negative, it is reached in a longer time, T2. Action potential duration. The longer the action potential duration, the longer the time it takes to return to phase 4, thus reducing the firing rate. Effect of the autonomic nervous system on the pacemaker rate. Sympathetic stimulation increases the firing rate by increasing phase 4 slope, blue curve, compared to normal, black curve. Parasympathetic stimulation produces the opposite effect, red curve. Thank you.